Hi everyone, this is part 2 of your resonance series of videos, and in this segment we are going to look at the patterns within a structure that allow us to recognize whether or not resonance is present. So the first one I want to point out is one that we've actually already seen before, and that is lone pairs adjacent to a double or triple bond. And double and triple bonds consist of pi bonds, so I often will say next door to a pi system. So this lone pair is next door to an atom that is part of a double bond. And so this lone pair, really any of these lone pairs, could be involved in the pi system, the resonance delocalization of those electrons. We find our pi bond here, and then we look at the two atoms involved, and then we say, well, what atoms are next door to those involved in the pi bond? Well, both of these oxygen atoms are next door, so any lone pair on this oxygen or this oxygen could be delocalized in that pi system and participate in resonance. The lone pairs that are on the double bond cannot participate. And we'll see a little bit into the reasons why that is when we get to the subject of hybridization. So lone pairs adjacent to pi systems would allow us to draw curved arrows as such, moving the electrons around to give a resonance contributor. And we can do this until we have found all of the possible resonance contributors. So we've done these two examples before, so I won't dwell on them any more than I have to. Let's look at a different example to get a better idea of how this might look. Here is an example of an organic molecule that I've drawn with my bond line notation. And keep in mind that this end of the chain here is actually going to represent a CH2 group. So we have to keep in mind those rules of valence, and when carbon has a negative charge, it has an extra electron, so it would have its 3 bonds plus a lone pair. Okay? And to draw resonance for this, we have to look for our patterns, the lone pair adjacent to an atom that is involved in a double bond. So the electrons can move to form a double bond here, and then we will take this pi bond and move it to the next atom. So what this will look like, and I can color code this for you, that we will have a second bond here and a lone pair here. And this is where my negative charge will be if we account for formal charge. And this is as far as we can move those electrons. So this is as many resonance structures as we can have. If we look at them in terms of how much they contribute to a hybrid, we would look at whether or not the atoms all have an octet. That's number 1, which they all do. Number 2, we would look at the number of formal charges. They both have 1 negative charge. And then we would look at where those formal charges are. We want the formal charge, if it's negative, to be on more electronegative atoms, and if it's positive, to be on more electropositive atoms. So because this negative charge is on carbon in both of the structures, it's a tie. They are both equivalent after looking at those 3 criteria. And to draw the hybrid, we draw what's always there. So I have my framework. Sometimes I have a double bond here. Sometimes I have a double bond here. And sometimes I have a negative charge on each end of that. So overall I have a net -1 charge, and this would be my hybrid structure. And these hybrids give us some insight not only into the bond length, bond order, bond strength and whatnot, but also to the reactivity. So in organic chemistry, you would learn that both of these terminal carbons bearing a negative charge, according to the hybrid, could be nucleophilic and therefore a reactive site in that compound. The second pattern of resonance involves positive charge next to a lone pair or a double bond. So an example of that, similar to what we just saw, we can place a positive charge next door to a double bond, And now remember that positive charges are deficient in electrons. So we would be pushing the electrons toward the positive charge. And that's opposite of what we saw with the negative charge adjacent to the double bond. And this will give me, again, the same framework. My double bond will now be here, and the positive charge is now on the end of the chain because that's where we lost electrons from. We're taking electrons away from this terminal carbon here, and so that's where the positive charge comes in. To draw the hybrid structure of this, we would have our framework the same. Sometimes I have a double bond here, sometimes I have a double bond here, delta plus, delta plus. And I guess before we even drew the hybrid structure, we should have decided whether or not these were going to contribute equally to the hybrid. And they will, because both of the structures have one atom, one carbon atom, that does not have an octet of electrons. Both of the structures have one positive charge, and they are both on a carbon atom. So in all those terms, they are equivalent. There are some subtleties that you could get into in organic chemistry that would deem them to not be quite equivalent, but we're not going to go there in this class. So this is a double bond adjacent to the positive charge. Similarly, we could have a lone pair adjacent to a positive charge. And that would look something like this. We could have a positive charge here with a lone pair next to it. That lone pair would most often be on a heteroatom. So we're talking nitrogen, oxygen, sulfur, halogens to some extent. But we can move the electrons, the lone pair, again toward that positive charge to give me a resonance contributor. That lone pair now forms the second bond, and now we have a double bond. So when we rank these in terms of contributing structures, we would say, well, do all the atoms have an octet? Well, they do not in the top structure. So this structure is going to be worse than the bottom structure. So we can already determine that this is going to be my major contributor. We could look at some of the other criteria, like the number of formal charges. So I actually forgot the negative charge there. This has two formal charges where this has no formal charges. So again, this would be better. And then we would evaluate the position of those charges, but we don't need to do that because that's really the tiebreaker if both structures have formal charges. So this is the major contributor. This will be most like the true structure, and this is really the first time that we've seen an example where the two resonance contributors are not equivalent. And we can draw the hybrid still the same way. So I draw what is always there, my lone pairs, and what is sometimes there, dot, 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 and delta plus here, delta minus here. So this resonance hybrid does agree with what we would predict from the bond polarity, that this carbon atom of my so-called carbonyl group, the CO double bond is known as a carbonyl, will bear some partial positive charge. And like I said, that does coincide with what we would predict based on the bond polarity. So resonance theory agrees with that. The third pattern of resonance is a double bond between two atoms of differing electronegativity. So this is an example where we have a double bond between carbon and nitrogen, and because nitrogen is more electronegative, it's pulling on those electrons a little bit more than carbon is. So we could take that to an extreme and say give those electrons to nitrogen to result in this resonance contributor. And we can again evaluate these contributors in terms of their contribution to a hybrid. Do these atoms all satisfy the octet rule? Well, in this structure they do, in this structure they don't. So this is the major contributor because all atoms do satisfy the octet. This would be secondary, still contributes, but to a lesser extent. This also has a larger number of formal charges than this one. So in terms of my hybrid structure, what is always there, always have at least one lone pair. Sometimes there I have a double bond, sometimes I have a delta minus, delta plus. So overall, this is a neutral compound, but we can take it to an extreme. And again here we see resonance agreeing with the bond polarity that we would predict. There's a partial positive charge at this carbon center. Again, plays into the reactivity that we see for some organic compounds in that field of study. I will also point out this is the case for our carbonyl. So this will be about the opposite of what we saw a few minutes ago, where we can take the double bond and move those electrons onto that oxygen. Again, taking it to an extreme, much like we saw for the nitrogen example here. So hopefully you recognize this as similar to what we saw a minute ago with the positive charge adjacent to a lone pair. These patterns will play off of one another. The final pattern of resonance is a much more specific example, and this is when we have alternating single, double bonds. So we go double, single, double within a ring system. And this is a particular type of organic compound known as an aromatic compound. And they have this classic single, double bond pattern most of the time, and will be stabilized by resonance. So we can move these double bonds around the ring. We cannot exceed the octet for carbon here, so we must move electrons, and we must move electrons. So overall, we end up getting a structure that looks very, very similar. We have just changed the positioning of those bonds. And if we draw a hybrid of this, specifically this is benzene, so sometimes I have a double bond here, 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 and there are no partial charges involved, whatnot, but this is sometimes abbreviated as just a simple circle in the center of the ring to indicate that those electrons are all delocalized. They are spread out across all of those bonds. So the bond order of the carbon-carbon bond in benzene, we can actually determine. So these 3 bonds are shared over 1, 2, 3, 4, 5, 6 bonds total. So 3 over 6 is 1/2. So there's always a single bond plus half of a second bond. So the bond order is 1.5 for all of the carbon-carbon bonds in benzene. And again, this is known experimentally. So resonance theory is supporting the experimental data. Thanks for hanging in there for this video on the patterns of resonance. If you have any questions regarding these 4 patterns, please let me know. But there are a couple worksheets out there for practice, so give those a try.